How are we doing, my lovely kiddos? So today our lesson is going to be on geometric definitions and two-column proofs. So just kind of an intro to some of these things. Our learning targets are we're going to look at distinguishing between undefined and defined terms, and we're also going to look at using properties to complete algebraic two-column proofs. So those are our two learning targets. So one thing to understand about geometry is that it is what we call an axiomatic system. Okay, an axiomatic system. What that means is that you start off with a few basic assumptions or definitions that everyone just kind of assumes to be true, and from there you build on those things to create new theorems, new ideas, new proofs based off those agreed upon facts that everybody can kind of go with. Okay, so geometry, it's important to agree on your meanings of your definitions to make sure that everybody's on the same page. So one thing about a definition is that it has to be understood very easily. Okay, whatever words you use to express it must be words that people already know and understand. So looking at these two definitions right here, compare these definitions. A definition for a fountain: a roundel that is very wavy of 6 argent and azure. And a gage, a belt that is worn over the right shoulder and used to support a shield. So which of the two definitions above is easier to understand and why? So go ahead and give that some thought, pause the video, and then we'll go with the answer. All right, so let's go ahead and look at the answer to number 1. And it says that the one with the best definition, easiest to understand, is the definition for gage, because all the words used in the definition are already easy to understand. You understand what each of the words in this definition are, or you should. Whereas the definition for fountain has a lot of new vocabulary words that aren't words you probably know, or you don't know enough of them to understand what a fountain is. Okay, so moving on, one thing to realize about vocabulary in geometry is that it's important to use vocabulary as a foundation for new terms. So you have to understand some basic terms early on and then use those terms to define new vocabulary words you might not know. And then once you know those, you use those to define new words. So in geometry, we have basic terms that we use. We call these fundamental undefined terms. And the basic ones we're going to use are point, line, and plane. So hopefully you have an understanding already of those three, and we can use those three terms in definitions of new terms in order to understand what some of the new vocabulary terms are. So using these three terms, point, line, and plane, do your best to define these new terms: ray, collinear points, and coplanar points. See if you can use these 3 points and create your own definitions for array, collinear points, and coplanar points, and then we'll go over it. So pause the video, give it some time to try, and then we'll see what you can get. So definition for array. So array might be a term you're familiar with. Maybe these are terms you've never heard before, but array is a part of a line. Okay, so we're using this defined term line right here. All right, but we say array is a part of a line bounded by one endpoint and extending infinitely in one direction. So to give you a visual picture of array, okay, so if we draw a line that we know first, okay, so this is a line. So using a line, we're going to say, okay, an array is part of a line bounded by one endpoint. Okay, so we're going to stop at that endpoint, and then we're going to extend infinitely, which means forever, in one other direction. So the blue segment, or the blue part right there, is array, whereas the red part is a line. Okay, so we use the definition and the term line to help us define array. Collinear points are points that lie on the same line. So you think co-pilot. Co-pilots are two pilots that fly the plane together, right? So collinear points are points that are together on a line, just like co-pilots fly the plane together. Collinear points are on a line together. So example visually of collinear points would be like this right here. So you've got a line, and all three of these points are on that line, so they are called collinear points. And similar to that, coplanar points, notice the root word here is line. For coplanar, the root word is plane. So now we're not talking about points together on a line, we're talking about points that are together on a plane. So if we draw a plane, any points that are on that plane together would be considered coplanar points. Coplanar points, points that lie on the same plane. So we've used the term points, the term line to help us define these new terms. Okay, so now after we've defined these terms, now we can use these terms to define even more terms. For example, right, an angle is defined as a figure formed by two rays with a common endpoint. So we just learned about a ray. Now we can use that term to define another one. So if we draw a picture of it, you can see if we draw an angle, it's if we take two rays, so we got one ray here, and it says the rays have to have a common endpoint. So the other ray has to also use that endpoint. So when we draw two rays that have the same endpoint, that creates an angle. So again, we use the term ray to create a definition for an angle. All right, so for 3A and B, define each term using already defined terms. So see if you can come up with definitions for complementary angles and supplementary angles using some of the terms that we already know. So you can use point, line, plane, ray, collinear points, coplanar points, and angle to define complementary angles and supplementary angles. Give those a try and then we'll go over it. So definition for complementary angles are two angles whose measures have the sum of 90 degrees. Sum meaning they add up to 90. So that can be a 30 and a 60, that adds to 90. Could be a 70-degree angle and a 20-degree angle. Anything where they add up to be 90. Could be 89 degrees and 1 degree. Anything that adds to 90 will give you two complementary angles. Supplementary are just two angles that add up to be 180 degrees. So that could be 180, could be 110 and 70. Any two numbers that add to 180 are supplementary angles. All right, so when discussing proofs, one thing that's important to understand about proofs is you have to use what we call deductive reasoning or deduction. Okay, so to do deductive reasoning, you must have a starting point. Okay, so you've got to have some point you start at, and then from there, you use your knowledge of whatever starting point you're at to make a decision about something else or make a conclusion about something else. So a conclusion based on deduction can't be made unless you have some kind of established starting point to work from. All right, so one way to kind of think about this is the game Uno. So if any of you are familiar with Uno, okay, so let's say you've got a starting point, right? Down on the ground or on the table is a red 1. All right, and your goal is to get to a green 8. All right, so to play Uno, in order to play on a red 1, you have to either play a red card or a card that has a number 1 on it. It can be any color as long as it's got a 1 on it. But if it's not the same number, it has to be the same color. So see if you can pause the video and see if you can get from a red 1 to a green 8 using these three cards down here. Just put them in the order that'll work and give that a try, and then we'll go over it. Okay, so this is the way you would have to put them in order. The only thing you can play on the red 1 is the blue 1 because you don't have another red card, so it has to have the same number. Then from the blue 1, the only thing you can play is a blue 5. And once you play a blue 5, the only thing you can play is a green 5, and then a green 5 will get you to a green 8. So notice how we take the starting point, and we've got the end in mind that we're trying to get to, and we've got to use the steps in between to go from our initial step to something else, and then move on from that to something else, and move on from that to something else. So this is kind of a visual picture of how deductive reasoning actually works. So looking at this problem right here, whenever you solve algebraic equations, you're using deduction, whether you realize it or not. You can use properties to support your reasoning without having to prove that the properties are true. All right, so one operation or property is used for each step of the equation. So down here, all right, I want you to show how you solve this equation, just step by step, and then out to the side of each step, name the operation or property that you used in each step. And over here are a few that you can look at to help you. Again, these are in the notes that you can kind of see the properties that you might use. So these might be your justifications for your steps. So pause the video and give this a try, solve the equation, and then out from each step of the equation, write the property or operation that you used. And then we'll go over it. All right, so here in the first step, they just rewrote the equation. And then from this step to the second step, they added 1/2 x to both sides, which made 4.5 x on the left. So because you added something to both sides, that is the addition property of equality. Then from there, notice the 9 is no longer on the left side. And over here, there's 9 less. So they subtracted 9 from both sides. So that's the subtraction property of equality. Those properties just say that you can add to both sides of an equation, or you can subtract from both sides of the equation. And then from here, since it's 4.5 times x, you divide both sides by 4.5 to get x by itself, and 9 divided by 4.5 gives you 2. So because you divided both sides by 4.5, that's the division property of equality. So this is how we justify and explain our steps to each of these equations. Now, most of you probably just do this naturally, but it's important and helpful to understand this process of justifying each of the steps in an equation, because in geometry, when we do proofs, you'll have to be able to justify each of your steps. All right, so I appreciate you all paying attention, and let me know if you have any questions.